Welcome, ladies and gentlemen, to your MN30 notes, where we're going to use proportions to solve geometry problems. This is connected to your section 6.2 in your textbook. And before we get started, we're going to talk a little bit about some proportional properties. That's really hard to say, proportional properties. The first is reciprocal property, and kind of taking a step back when the last time we talked about reciprocals, which really was when we were talking about perpendicular slopes of lines, where we would take the opposite reciprocal to find a equation of a perpendicular line. So just kind of taking it to a concept that we've studied in the not so far past. But this reciprocal property is just where you're going to flip the fraction for the proportion. So a over b is equal to c over d here. Then b over a is equal to d over c. This next property is where you can interchange your means. So it's a over b is equal to c over d. Then a over c is equal to b over d. What you're going to start realizing, while these properties, we use them all the time, it's what makes proportions so powerful, where you can solve them a multitude of ways, but it also causes frustration for students because there's not just one way of doing or solving a proportion, and it's because of these properties. This one right here, number 3, the last property we're going to talk about quickly, is one that we use a lot, and this is the one that I'm going to reference back to quite a bit in this note guide. It's where it's a over b is equal to c over d. Then you can take, to give you the same proportion, you can add your numerator and denominator, so a plus b all over your denominator of b. So if that's the case, then you can say c plus d. So add your numerator and denominator is all over your denominator. So whether it's this proportion or this proportion, these are going to give you the same result. And rather than talking too much more about that, let me just show you how that's going to work out down here in example number 1, where it says in the diagram, the side AC over side DF is going to be equal to the ratio of BC over EF. And down here, it says because AC over DF, so the side AC over DF is going to equal the side BC over EF, then, and you can really literally just substitute in the information you know. So AC right here is 12, so that's why they have 12 right here. DF is 18, which is right there. So what they're just saying is the ratio of the side lengths, AC to DF, is going to equal the ratio of the side lengths of CB, which is 9, right here, over x. So you're just creating a ratio and, or excuse me, a proportion so that you can solve for x using the ratio of the sides. So what do we do? Of course, when we have something that looks like this, 12 over 18 equals 9 over x, we can just cross multiply and solve it. That's what it's saying right here. So you end up with 12x equals 9 times 18, 162. Divide out by 12, and you get x is equal to 13.5. So that is one way of setting up a proportion with the ratio of sides. So to find an unknown side length of similar triangles. And here in example number 2, it says use proportions with a geometric figure. It says find the length of JL. JL is right here. And find the length of JH, which is the full length, so from all the way from J to H, and then GH. GH is right here. Now I'm gonna erase that for a moment. I'm gonna actually put variables where I need variables to be. So for instance, let's just say we have this x. How about we say from G to H is y, and from J to L is z, just so that we have a couple variables there. And we can find whichever one you want to find, and there's more than one way of doing this, as I mentioned earlier. But I think just looking at it for ease of explaining, I'm gonna move this around here. Let's solve for y first. And what we're gonna do is I'm gonna do all of finding y in blue here. So we're gonna create, or we're gonna look for ratios that can be compared to make a proportion. So I can say JK, this length right here, over this length right here, which is KL, is going to equal the length of JG over GH. So if that's the case, now I can substitute things in that or the values in that I want, and I'm going to erase it so it doesn't get too nasty here. So JK is 15 over KL, which is 12. That's going to equal JG, which J to G, careful you add those together, that's going to give you 20 over GH, which we don't know, and that's where we put our variable y. So it's really a good idea to put a variable in where you don't know the answer. That's why it's called a variable. It's the unknown. Here we want to cross multiply to solve, so we have 15y equals 240. You divide out by 15, and you will end up with y is equal to 16. Now, you probably heard me pause there for a minute, and it's because I just kind of double-checked my own notes, and I set it up differently in my notes. So I want to say that there's so many different ways of setting these up, these proportions, and really whatever is going to work best for you. And you can try different ways and see if you do get the value of GH, which is 16. JH, or JL, whichever one we want to do first, we can. And I'm going to let's just say JL. So I'm going to say this Z, I'm going to start with my unknown this time, Z over 12. Now let's not do that, because if we go across, we need to, I'm just looking at what we have here. Let's do this one. Z is to 2, because this is one people don't really notice. Z is to 2 as 15 is to 5. And you can do that where you have this little piece right here, this is to this little piece here, as JK over here is to KG. We only can do that assuming these are similar triangles within each other, which causes these two lines to be parallel. So we're kind of doing a jump of faith here, but because they are similar triangles as they mentioned up above, we can assume this. So we have 5z is equal to 30. So z is going to equal 6. So if I go over up here where it says JL we've just found is 6, and JH we know is going to be 6 plus 2 more, which is going to be 8. Okay. And again, there's more than one way of solving these. Try different ways and just kind of get used to all the different ways you can set up the proportions. We're going to go over here to example number 3, which is dealing with scale figures. It says the length of the key in the scale drawing is 7 centimeters. So from here in this drawing, from here to here, is 7 centimeters. The length of the actual key, so the actual key is 4 centimeters. What is the scale of the drawing? And we have kind of a broken down way of understanding it down here. It says to find the scale, so I'm reading down here now. To find the scale, write the ratio of the length in the drawing to the length of the actual length. And I'm going to just write actual. Oops, except I need to spell it right? Actual length. Then rewrite the ratio so that the denominator is 1. And let me just kind of explain this here in right down here. It says the length in the drawing to the length of, or the actual length. I'll just put actual. I'll write length here so we don't get confused. And the length in the drawing is 7 centimeters. And the actual length is 4 centimeters. So what this is saying is for every centimeters in the drawing, it's going to be 4 centimeters in reality. And what you want to do, as it says, is write the denominator is 1. So when we're talking about scale, we tend to always write it as almost a unit measure. I think that's the other thing, or not I think, that is what we tend to say in math, a unit measure, which is always with the denominator of 1. And what you do, and I'm just going to bring this over here, is take 7 divided by 4, which is going to give you 1.75. So that's going to be your scale, 1.75. And what that essentially means is that 1.75 centimeters, oops, um, the drawing is equal to 1 centimeter in the actual or real. Okay, so for 1.7 centimeters in the drawing, it's 1.7, or excuse me, 1 centimeter in the actual picture. But this right here, this is technically what we would call the scale, and the scale really is just comparing two items. Down here, it says use a scale drawing. And I know now with MapQuest and everything, Google Maps, we don't use scales as much in maps, but we, it still comes in handy. It says the scale of the map of the right is 1 centimeter equals pretty much 8 miles. So for every 1 centimeter, it's 8 miles. Find the actual distance from Westbrook to Cooley. So we're looking for Westbrook here to Cooley. Now, I don't know if you have a ruler handy, and I don't know if I can do this. I'm going to try. I'm going to bring down my ruler. Actually, I've never done this before, so it should be interesting. Yeah, as typical, it doesn't really want to work for me. So let me just ad lib and tell you that when I measure this from here to here and then here to here, it's going to be about 3 centimeters. Okay, so it's like 2 centimeters and 1 centimeter to give me a total of 3 centimeters. So what I can do over here is I can say, hey, you know what? For 1 centimeter for the scale over 8 miles, this is real, right? Then we can do in the scale drawing or the picture, we found that it was 3 centimeters, and we want to know how many miles. And so this again is just a ratio, or a proportion, excuse me. So it's 1 centimeter to 8 miles is equal to 3 centimeters to X miles. We don't know. So we're going to cross multiply. And down here it kind of talks a little bit more about all of that right here in the solution. I kind of jumped the gun here because I was so excited. 1 centimeter times X is X equals 8 times 3, which is 24. So I'm just solving this proportion that I set up. So the actual distance from Westbrook to Cooley is 24 miles by using proportional reasoning. And I've got to tell you folks, proportions I use all the time, whether it's at home, at school, everywhere. And the key is to make sure you use your units, because if you don't use units, it makes it very, very difficult to know if you're setting up your proportion correctly. So thank you for tuning in on this note guide. We'll take questions, any questions on this note guide tomorrow in class.